Okay, once you have your data, you should have a table of numbers that looks something like this, except for that all of these cells should be filled out. I confess that these numbers are completely fake data because I didn't actually go measure trees yet. So, but once you have your table filled out and you have the log 10 transformed height and the log 10 transformed diameter, I want you to do two things. The first is to create a scatter plot of height versus diameter, or the log 10 transformed height versus the log 10 transformed diameter, and insert a regression line on that scatter plot. And the second thing I want you to do is to compute statistics of that regression line. So let's start with the chart. I'm going to highlight the data. I'm going to insert chart. And I'm going to clean up this title here because it's kind of ugly. Okay, so here's our scatter plot where we have the log 10 transformed diameter on the x-axis, the log 10 transformed height data on the y-axis. Here are the data for our 6 trees, okay? So this kind of a plot is called a scatter plot. And I want to add to this a regression line. And a regression line shows how we can predict height as a function of diameter. So let's edit the chart and go to customize series, add a trend line, and then include the equation for that trend line. Okay, so here's our regression line right here. And this regression line has 2 parameters. The first parameter is this number right here, and it's called the intercept. The intercept is where that line crosses the y-axis when x is equal to 0. So here's x equal to 0. The line is crossing at a value of y of something just less than 1. And you can see that value is actually 0.934, right? The second parameter is this number right here, and it's the coefficient of x, all right? This parameter is the slope of this line. And the way to interpret this parameter is if we increase x 1 unit, so say if we go from negative 0.5 to positive 0.5, the y value raises or increases 0.687 units. Okay? Now what I want you to do is use Google Sheets to compute statistics of that parameter right there, of the slope parameter. And the statistic that I want you to compute is the standard error of that estimate. Okay? I don't know how to do this, or I didn't know how to do this till yesterday, but here's how I learned to do it. I just Googled how to compute standard error of the slope Google Sheets. And I got some hits, and I knew what the slope function was, but I'd never seen this linest function. So I clicked on it, and given partial data about a linear trend, this function calculates various parameters about the linear trend. That looks pretty good. So let's see what it computes. It computes, in addition to the intercept and the slope, it computes statistics for those parameters, including the standard error for each coefficient. These are the parameters. The coefficient of determination, standard error of the y values. We don't care about any of this. This is what we want right here, the standard error for the coefficient, right? That is the slope. So to use this, we need to put in the y data. We need to put in the x data. I don't really know what these things are, so I'm going to read down here. Calculate b. Given a linear form, mx plus b calculates the y-intercept. So in other words, do we want this function to return the intercept? Yes, we do. Second, verbose, optional, false. So this is a Boolean, meaning that you'll either input true or false, and it's false by default. And this, if you put true, it will return the additional regression statistics. That's this stuff right here. This is what we want because we want the function to return that value. Okay, so let's go back to our tree allometry. Let's set this up right here. Equals len est, and then I need to put in the y column, the y array. I need to put in the x array. I want to return the intercept coefficient, so I'm going to write true, and I want to return the statistics of the coefficients and of the intercept, so I'm going to type true, and there we go. So what are our values? These are the parameters, or I should say these are the estimates of the parameters, and these parameters are the slope, or beta 1, and the intercept, or beta naught. Okay, this is the standard error, and these statistics are the other statistics specified in that page that we don't care about. Okay, in another video, I'll explain what the standard error is, but we want to compute from the standard error a statistic called the 95% confidence interval. So it's the boundaries of the 95% confidence interval is the boundaries of this estimate right here. In another video, I'll explain in more detail what that 95% confidence interval is. But in order to, a good rule of thumb is that the 95% confidence interval of an estimate is that estimate plus or minus 2 times the standard error. All right. So if we can put that here, lower, upper, the lower bound of that estimate is equal to that estimate minus 2 times the standard error. And the upper is that estimate plus 2 times that error. All right. This estimate, or this rule of thumb of 2 times the standard error, is really only good if you have a fairly large sample size. And we only have 1, 2, 3, 4, 5, 6. Our sample size is 6. And that means this is not a great rule of thumb. So let's use an exact value. In order to use the exact value, we need to use what's called the inverse t function. So let me just show you the inverse t function here. T inverse 0.05, that's the complement, and we want the 95% confidence interval. So the probability outside of that is 0.05. And then we need to input a degree of freedom. Okay, I said this works, that this function will return something close to 2 if this number is high. So let's put something like 1,000. 1.96. All right. But our degree of freedom is not 1,000. Our degrees of freedom are the sample size minus 2. So the sample size is count that's going to count the elements in that array minus 2. All right, 2.77. You can see that 2.77 is not a very good approximation. All right, but now we need to subtract that and add that to our estimate. So let's add that in here. It's our estimate minus t inverse times the standard error. Remember, it's a number close to 2 times the standard error, then we subtract that from the estimate. All right, and here we want the estimate plus T inverse. 0.05 is the probability, and our degrees of freedom is count our sample size minus 2. And we need to multiply that by the standard error. All right, so now we have the lower and the upper confidence interval of this estimate of the slope.